Hi everybody, today we're going to dive into a video that explores our next unit, which has an awesome word that describes it. It's called stoichiometry. So stoichiometry in a nutshell means we are measuring, that's what the metron part of stoichiometry is, and we are measuring elements, and that's the stoichion part. So this is an old Greek word. Basically what we're doing is we are making some predictions about the quantities of different things in a chemical reaction. Before we begin today, it would be wise to have a periodic table so that you can identify charges of ions and then you can combine them to form different compounds. And we are going to need to write some balanced chemical equations for this. So it turns out that the coefficients in our balanced chemical equations, like this 2 and this 2, and there's a 1 here that's not written, those coefficients allow us to make some relationships that ultimately become conversion factors, and those conversion factors are really important for doing dimensional analysis. So if we look at this equation that we have here, the decomposition of water, we know something. We know that 2 water molecules will split into 2 H2 molecules and 1 O2 molecule, right? And so what if, instead of just having 2 water molecules, what if I had, let's say, 12 water molecules, or 2 times 12, 2 dozen water molecules? Well, 2 dozen would split into 2 dozen H2s and 1 dozen O2s, right? But what if I had a mole of them? We would say that 2 moles of H2 would split into 2 moles of this and 1 mole of this. And remember, a mole is just a number that means 6.02 times 10 to the 23rd power. And it turns out that because when we get information off of the periodic table, it is given in grams per mole, it's a lot more logical and it makes our life easier to relate these quantities in moles than in single elements or compounds. So, as a reminder, what this really means is that 2 moles of H2O, if it reacts completely in a decomposition, is equal to 2 moles of H2, and that's also equal to 1 mole of O2. All of those are equivalent, which means we can write those as conversion factors. So let's take a look at the first 2 parts of that. Let's look at 2 moles of water being equal to 2 moles of H2. So what if I elected to divide both sides of that by the same thing? What if I elected to divide both sides by 2 moles of H2O? Well, 2 moles of H2O over 2 moles of H2O, this just cancels out. This gives me the value 1. And that 1 is equal to a fraction. It's equal to the fraction 2 moles of H2 over 2 moles of H2O, which you'll notice is what we see right here. So we can write equalities as fractions. And you'll notice we can actually flip that fraction upside down, and if you're wondering how we do that, let me just erase some of the information that I have here. So what if instead of dividing by 2 moles of H2O, what if instead we divided by 2 moles of H2? This would be over 2 moles of H2. Again, 2 moles of H2 over 2 moles of H2, this is also equal to 1, so we can use it in a dimensional analysis conversion factor problem. And you'll notice 2 moles of H2O over 2 moles of H2 is right there. So we can basically rewrite these equalities as conversion factors, and every time we write them as conversion factors, we get 2 because we can write them upside down or right side up. So today's little note guide is going to give us a little bit of practice writing chemical equations, balancing chemical equations, and then we're also going to complete mole ratios, and we're going to write all the possible mole ratios for our reaction. So let's say that we decompose aluminum oxide by electrolysis. So aluminum oxide, Al is a +3, O is at -2, so we'll get Al2O3. Decomposition of a binary compound simply gives us the individual elements. So we have aluminum, we also have oxygen, but remember oxygen is diatomic, so we'll put a 2 there. Now it tells us that's melted, so we know that's a liquid aluminum oxide, but honestly the state of matter isn't terribly important for what we're doing today, so I'm just going to worry about balancing here. Now you'll notice that we have 3 oxygens on the left and 2 on the right. You can absolutely make your list if you'd so desire in the middle. but I know that those are going to have the lowest common multiple of 6, so I'm going to throw a 2 here and a 3 here, which means I need a 4 in front of aluminum. So those coefficients are extremely important for stoichiometry. In order to do stoichiometry, you must have a balanced chemical equation every single time. So if you're struggling with your equation writing, or your naming, or your balancing, now's a great time to get that cleaned up, see us for help, do some extra problems in the textbook, right? We need to have that cleaned up because we need those balanced chemical equation conversion factors, or excuse me, coefficients to write out some conversion factors. So let's do the ones that relate aluminum oxide. Anything that includes aluminum oxide, we are going to do in purple. So we know that 2 moles of aluminum oxide, and that 2 comes from the coefficient, 2 moles of aluminum oxide, which is Al2O3, is equal to, so I can write it as a fraction, 4 moles of aluminum. And actually, I'm going to rewrite this in a different color in terms of the coefficients because these numbers came from the coefficients from the balanced chemical equation, right? So that 2 and that 4 came from those 2 spots. And of course, if we can write it that way, we can also write it the other way, right? So 2 moles Al2O3 over 4 moles of Al could just as well be written as 4 moles of Al over 2 moles of Al2O3. So 4 moles of Al over 2 moles of Al2O3. But we could do more in purple, couldn't we? We could also relate aluminum oxide to oxygen. So there's a 2:3 ratio of aluminum oxide to oxygen. So I could put my moles of aluminum oxide over my moles of oxygen, or O2, or I could write my moles of O2 over my moles of aluminum oxide. And in both cases, I would use a coefficient, right? And we see that the coefficient for aluminum oxide is 2, and the coefficient for oxygen is 3. So we're going to keep those coefficients with their appropriate compounds, and we get these 2 conversion factors that we could use in a dimensional analysis problem. The last thing we need to do is relate aluminum to everything, right? So we'll do that in green. If I want to relate aluminum to oxygen, I know that I can put my moles of aluminum, which is Al, over my moles of oxygen, or I could put my moles of oxygen over moles of aluminum. Either of those would work. They both have coefficients. Notice aluminum always has a 4 in front of it, so anywhere I have aluminum, I'm going to put the number 4. And anywhere I have oxygen, I am going to put the number 3 because that is the coefficient in front of oxygen. And you might ask, well, wait a second, we haven't related oxygen to anything, right? Don't I need to pick a color for that? But look, we've already related oxygen to aluminum. We did that in green, and we already related oxygen to aluminum oxide. We did that in purple. So we are good to go. Let's try again. This time we are going to do the decomposition of solid mercuric oxide. So solid mercuric oxide. We know that mercuric is Hg plus 2. Oxide is O minus 2, so that's simply going to give us HgO. We need to decompose. Binary compound decomposing simply makes the element by itself, plus the other element by itself, but O is diatomic. We will definitely need to balance, right? So we have 2 O's on the right-hand side. We'll need 2 there, 2 there, and now it's helpful to write this 1 because we're going to use that coefficient as we start making our relationships. So let's do orange for anything that relates to HgO. We can relate HgO to Hg, right? We can put HgO in terms of moles of HgO over Hg, or we could put moles of Hg over moles of HgO. And those both have numbers in front of them, right? There's a 2-to-2 relationship going on there. And this is a great time to talk about the fact that that could simplify, right? You might notice that 2 over 2 would simplify to 1 over 1. We don't want you to simplify. The reason we don't want you to simplify is we want these numbers to match the coefficients that you see in the balanced chemical equation. So because those are 2 and 2 there, we don't want you to write them as 1 and 1. We want you to keep them as 2s. Now mathematically, obviously you can leave them out of your calculation because it's just 2 over 2, which is the same thing. But in terms of showing your work, we'd like you to leave the 2s there so that we can see where it is that you got those numbers from. And I'm just going to slide this up so it's a little bit nicer. Okay, let's relate HGO as well to oxygen. So we'll do this in orange because it's still HGO. So we know that we could put moles of HGO over moles of oxygen, and oxygen is O2, or we could flip that, right? We could have moles of oxygen over moles of HGO. They both have a coefficient. The coefficient in front of HGO, you'll notice, is 2. The coefficient in front of oxygen is 1, and I'm keeping that coefficient with the appropriate compound. Finally, we could relate, and let's do this one in pink, we could relate Hg to everything else. Hg has already been related to HgO, so we don't need to do that way. We do need, though, to relate it to oxygen. So we could put moles of Hg over moles of O2, which is oxygen. We could put moles of O2 over moles of mercury, right? And they again have coefficients. There's a 2 in front of Hg. In both places, there's a 1 in front of oxygen. So those are all of our possible mole ratios for that equation. Let's try one more. So let's do the reaction where we have ammonia gas reacting with nitrogen monoxide. So ammonia gas, remember, is NH3. Again, I don't really care about its state of matter for today's purposes. It's reacting with nitrogen monoxide, so that is simply no. And we are going to produce nitrogen gas and liquid water, right? So we know that nitrogen gas is N2 because it's diatomic. It wants a friend. And we have liquid water. So we will need to balance this. This one looks a little bit trickier to balance, but I'm going to start off with my H's, right? Again, if you want to make a list, feel absolutely free. I know that in terms of H's, I have 3 of those on the left and 2 on the right, so we again need a lowest common multiple of 6. That means I'm going to put a 2 here, and that means that we are going to need a 3 here, right? And to match those 3 oxygens on the right-hand side, well, I'm going to need 3 nitrogens on the left-hand side. 3 NOs on the left-hand side. And then if you look at your hydrogens in total, we have 2 times 3 is 6. We have 3 times 2 is 6, so hydrogens are good. If you look at your oxygens, we have 3 times 1 and 3 times 1, so oxygens are good. In terms of nitrogens, we have 2 times 1 and 3 times 1 is 5. So we have 5 on the left and we have 2 on the right. Looks like we have a problem, but remember, we don't. We're going to make this 2.5, and then we are going to double everything to make everyone happy. So 2 is going to become 4, 3 is going to become 6, 2.5 is going to become 5, and 3 is going to become 6. I'll rewrite this one so we know what it actually is. Okay, so we have our balanced chemical equation, and from that, we are going to write a whole host of these conversion factors, right? And there are going to be more because we have more things to relate. So let's start on the left-hand side, and we'll take it from there. We'll start in pink. So I'm going to relate ammonia to everything else in pink. I need to relate ammonia to nitrogen monoxide. So I need to put moles of ammonia, which is NH3, over moles of nitrogen monoxide. And of course I need to flip that, right? So I need to have moles of nitrogen monoxide over moles of ammonia. We also need to relate moles of ammonia to moles of N2. So we can do moles of ammonia, NH3, over moles of N2. We'll start a new column. We could do moles of N2 over moles of ammonia. We'll get the coefficients in a second. We need to relate NH3 to H2O, right? So we could put moles of NH3 over moles of H2O. Or we could put moles of H2O over over moles of NH3. And of course I need coefficients for all of these relationships to make them true, and those coefficients are what we have in red. So you'll notice anywhere there's an NH3, the coefficient is 4. I'm going to plug in a 4 anywhere I see NH3. So there's an NH3, here's an NH3, here's an NH3. These all have NH3 because they are all pink. So our color coding is working out for us. Now let's go through. Everything that has an NO gets a 6 in front of it. So this gets a 6, and this gets a 6. And yes, that could simplify, but we're going to leave it as 4 over 6 because we know it came from the coefficients. Anywhere that has an N2 gets a 5. So this gets a 5, this gets a 5, and anywhere that has water gets a 6. And again, where are those numbers coming from? They are simply coming from the red coefficients that you see that we use to balance the chemical equation. Okay, let's do the same thing, but now we need to do it for nitrogen monoxide. We've already done nitrogen monoxide to ammonia, so we can skip that one. But we do need to do nitrogen monoxide to N2. So nitrogen monoxide is NO. We're doing moles of NO to moles of N2. And of course we could flip that, so we could do moles of N2 over moles of NO. We should also relate moles of nitrogen monoxide to water. So we could put moles of NO over moles of water. We could also flip that. We could put moles of water over moles of nitrogen monoxide. And that's all we have for nitrogen monoxide because we've already done the relationship to ammonia in pink. So now we can come through, and anywhere that we have a nitrogen monoxide gets a 6. Right, so there's a 6 here, there's a 6 here, there's a 6 here, and there's a 6 here. You'll notice that N2 has a 5 in front of it, so both of the ones that have an N2 are going to get a 5. And you'll notice that water has a 6 in front of it. So here's a 6, and there's a 6, and again, we are not going to simplify. And let's also do one more color. What haven't we used? Let's pick orange. We need to relate N2 to various things. So N2 has already been related to NH3. It's already been related to NO. So we only need to relate N2 to water. We need to put moles of N2 over moles of water. And we also need to put moles of water, or moles of H2O, over moles of N2. Voila. And you'll notice that N2 has a 5 in front of it, so there's our 5, and H2O has a 6 in front of it. And so now we are good to go. We probably won't spend a great deal of time writing out all of these different conversion factors like we did in today's practice, but it's very important that you recognize how many different conversion factors you can get just from a balanced chemical equation, because we're going to need those whenever we dive into stoichiometry, starting with the next video.